So we're continuing with the prelude to the definite integral. Now we have all this notation and terminology set up with, you've got a subinterval, you partition it by picking endpoints of a bunch of little subintervals, you pick a sample point inside each interval. At each sample point in each of the intervals in the partition, you evaluate some function that you're interested in. In our example, it was velocity. You multiply the velocities at the sample points times the widths of the subintervals, so that was velocity times a change in time. It gave you an approximation of the change in position, so little displacements. We added up all those little displacements. Called that a Riemann sum, and it's an approximation for the total displacement. I'd like to start with another example so that you don't think that this just applies to velocities and displacements. So let's start with a circular rod, which I'm not really picturing this big, but I have to draw it this big to draw other stuff. So assume this is 1 meter long. I'm going to set up an x-axis so that this is the x-axis, or this rod is along the x-axis. Here's x is 0, here's x equals 1 meter. I want to pick a cross-sectional area. I'm assuming it's a circular rod, so the cross-sections are circles. So the cross-section at any fixed x-coordinate, you fix an x-coordinate, so this is the x-axis. You fix an x-coordinate, and the cross-section is a circle, and I'm going to assume that the cross-sectional area, A, equals the cross-sectional area is 0.01 square meters. So in terms of radius, we won't use the radius, but just as an aside, this means the radius is 0.1 over the square root of pi meters. Okay. All right. So what are we interested in? I'm going to assume that at each fixed x value, if you look at the cross-section there, that the density of the rod at each point in that cross-section is the same, but so if I fix an x-coordinate, the densities at each point in the rod in that x cross-section are the same, but that the density may change as the x-coordinate changes. So in fact, I'm going to have it be more dense as you move from left to right on the rod. So I'm going to assume that the density is given by delta x, and it's just 1 plus x. Density is mass per volume, but it's kind of an instantaneous mass per volume. So this will be in kilograms per cubic meter. I'm going to assume that's our density function. So it means the density down here is 1 kilogram per cubic meter. And when you get to x equals 1, it's 2 kilograms per cubic meter. So this rod becomes more dense as you move from left to right. This is an instantaneous mass density. It's if you were at a point and you took a little, kind of think infinitesimally small, but that doesn't mean anything really, but took a little blob of volume around a point, and then you took the mass of that blob and divided by its volume, that should give you an approximation of this, and in the limit, we're assuming you get this. So it's an instantaneous density. Our question is, if you were given some values of the density at various points along here, how would you estimate the mass? Well, we're given the density everywhere, so if we pick some sample points, we can calculate it, and then we can calculate a Riemann sum to get the mass, or to approximate the mass. Why? Because this is how Riemann sums go. So we're going to chop up the rod into, we'll just pick a number. We're going to subdivide the interval from 0 to 1, so the length, into 5 subintervals of equal length. Well, then what will the length of each subinterval be? Well, the length of a subinterval in a partition is delta xi, but all of ours are going to have the same length, so I'll just write delta x. Well, if there's supposed to be 5 of them of equal length, and the total length is the length of this, we should take 1 minus 0 and divide by 5. So the length of each subinterval should be 1/5, or 0.2 meters. So we're going to take a partition where each subinterval in the partition has length 0.2. We start at 0, so it's easy to say what the partition is. Partition, these are just the x-coordinates, the set of x-coordinates in order. We'll do 0, 0.2, 0.4. We go up by 0.2 each time, 0.6, 0.8, and 1. That's our partition. So I'll set this up in a table like we did before. So our intervals we'll have the subintervals in our partition. We'll have 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, and 0.8 to 1. So those are the subintervals of our partition. We need sample points. And it's just 1 point from each of these subintervals. We're going to take something called the left Riemann sum. Well, there are at least 2 things we don't know here. One is what the left in left Riemann sum means, and the second one is we don't know what function we're finding the Riemann sum of, because we're going to take lengths of these subintervals. We want to end up with a calculation, an approximation of mass, so we have to think about what to multiply by. But the left Riemann sum, all this means, whatever our function is that our sample points are the left endpoints of each of the subintervals of our partition. So we just take the left endpoint of each subinterval because we're after a left Riemann sum. All right, and then we need the function that we're going to evaluate at those sample points. So the function that we want a Riemann sum of. And we have to think about what that should be in order to end up with an approximation of the total mass. We are going to take changes in x, so our intervals are x intervals. We're going to take changes in x, and we want to multiply by some function so that we get an approximation of the mass. So for instance, I'm not going to try to draw this in the correct spot, but if this is 0.2 and this is 0.4, this is 0.4, how would we approximate the mass in this region? Well, we've already decided we're going to use the left endpoint as a sample point. So what function do we need to multiply times this length to get an approximation of the mass of that little piece? Well, density is mass per volume. And yeah, this is an instantaneous density, but the approximation is that, well, you approximate the instantaneous density here, or you approximate the density everywhere as being the instantaneous density at your sample point, which means you're assuming, well, not assuming, but your approximation is that, this should be approximately what I get if the density were constant along here, and it were constantly what I get at this endpoint, which would be 1.2. So you take this density, the density that you're using here, 1.2, and you need to multiply it times volume, but to get an approximation of mass. But in the Riemann sum, you only multiply times the lengths, and we need to get the cross-sectional area in there. That means that the function we actually apply the Riemann sum to, or find the Riemann sum of, f of x will be, we're going to find Riemann sums of f of x, which will be the density times the cross-sectional area. So 0.01, the cross-sectional area, times the density. I'm going to drop the units. Well, maybe I won't drop them right now. This would come out in kilograms per meter. And then we'll multiply this by the change in x, so meters, and get kilograms, and get an approximation of this volume. So this is the function we're going to find Riemann sums of. So here we'll take 0.01 times 1 plus x, but I'm going to evaluate that at these sample points. So what do you get? You get a 0.01 times, you plug in x as 0. So you just get times 1. Here you get a 0.01 times 1.2. Here you get 0.01 times 1.4. Here 0.01 times 1.6. And finally 0.01 times 1.8. Okay. Down here, these, what did we put in our table before? It's, you put your little pieces of the Riemann sum. So you take this number and multiply times the width of the subinterval. And that's our approximation for the mass of each little piece. So that would be the approximate mass along that subinterval. And so, but each of these lengths is exactly 0.2. They're all the same. 5 subintervals of equal length. So down here you'll get 0.01 times 1 times 0.2. You just multiply each one by 0.2. Here, 0.01 times 1.2 times 0.2. And you continue. This gets really old really fast. Times, it won't fit, times 0.2. And finally, 0.01 times 1.8 times one last 0.2. Great. So those are approximations of the little amounts of mass above each of those subintervals, and you add these up to get the Riemann sum. So our left Riemann sum. Our Riemann sum using left sample points. A Riemann sum of this f of x with the given sample points. So our notation for that, R, I didn't call the partition anything. P, I'll call the set of sample points S, like we did before. Actually, let me not call it S. Let me call it L for the left sample points. So L for the left sample points of this F. Well, it's just this sum. You sum all of those things. What's the sum of all those things? We get 0.01. Actually, let me use our summation notation. This will be much shorter. So we'll sum as I goes from 1 to 5. What? Each one is 0.01. Then it's 1 plus. In the first subinterval, you use 0. Then you go up by 0.2 each time. So it's 0.2 times I minus 1. So for instance, when I is 1, on the first subinterval, you have 0.01 times, when I is 1, this would be 0, so just 1. And then in our Riemann sum, we have times of 0.2. When I is 2, all that changes is you've added a 0.2 in here. Each time I goes up by 1, you add another 0.2 to that term. That's what happened here, 1, 1.2, 1.4, 1.6, 1.8. This is the Riemann sum that we're looking at. For our approximation, this is our approximation of the total mass of the rod. Okay. But this is a constant, and this is a constant. Summing is linear. This is just 0.01 times 0.2. And then you have that sum. I'll write it out this time, but later we'll use one of our summation formulas. You get, so what we were getting is you get 1 plus 1.2 plus 1.4 plus 1.6 plus 1.8. What is this? Well, these two add up to 3. This adds up to 3, so that's 6, 7. So this is 0.002 times 7, so that's 0.014 kilograms. This is our approximation for the mass of the rod using subintervals of equal length and a left Riemann sum. Okay. How good is it? Hard to say, although we will try to calculate the exact mass in a minute. So it's hard to say, but we're going to try to do it. Okay, that's what we get for the left Riemann sum. What would have changed had we used a right Riemann sum? So that would mean you'd use the right endpoints of the subintervals as sample points. So what happens? Well, here you'd have 0.2. And here, 0.4. You always use the right endpoint. Here 0.6, 0.8, here 1. Of course, this changes down here. Now this would be a 1.2, a 1.4, 1.6, 1.8, and a 2. And it changes down here. 1.2, 1.4, 1.6, 1.8, 2. Great. So what will that give us for our Riemann sum? So another approximation for the mass. Well, so now I'll call these sample points the right. Ooh, that's going to conflict with our, well, it's a different R. I'm writing a very fancy script R. Let's not confuse that. Try not to confuse this with the R for Riemann sums. Our Riemann sum, the same partition, but now with the right endpoints as your sample points. Same function, our new approximation for the mass of the rod. Well, you can see what happens. Here we had this, which is the same as this, but all that's shifted now in this is that instead of 1, 1.2, 1.4, 1.6, and 1.8, we'll have 1.2, 1.4, 1.6, 1.8, and 2. So you can just see that what happens is we get 0.01, we still get times 0.2, but these things look like they've shifted over. Now the first one is 1.2, then 1.4, then 1.6, then 1.8, and then 2. So this is 3. This is 3 plus 2. This is now 8. So now we get 0.002 times 8, which is 0.016 kilograms. Our approximation is different. That's no surprise. We use different sample points. You use left endpoints of subintervals as sample points, and then you use right endpoints as sample points. You probably should get, I mean, it's unlikely that you'd get the same approximation. Over here we got 0.14 kilograms. Over there we got 0.16 kilograms. You might think, well, maybe we should always use the middle point. Maybe if we use the midpoint, we'd get the right thing or something better. That is not always true. In this case, that's going to be true. It doesn't have to be true, but it could be. So there's the midpoint Riemann sum. I do want to look at this. Also, you might think that if you pick the midpoint, you have to get the average of this Riemann sum and that Riemann sum. That is not true either in general. It can happen. In fact, it will happen here, but that's unusual. It's just, well, it's because our function is linear that it happens here. But let's calculate the midpoint Riemann sum and see what we get. So it's, again, you just take different sample points. And I'll write my sample points now as some fancy m. The midpoint of this interval is 0.1. The midpoint here is 0.3. Midpoint here, 0.5, 0.7, and 0.9. So what changes down here? Well, this becomes 1.1. This becomes 1.3. This becomes 1.5, 1.7, 1.9. And of course, it changes in the bottom row as well. 1.1, 1.3, 1.5, 1.7, and 1.9. What changes up here? Well, actually, I'll try to, I guess I can fit it in right here. So what do we get for our approximation with the same partition, but now using midpoints of intervals in our Riemann sum? So taking the midpoint Riemann sum, this again gives us an approximation of the mass. In general, there's no reason to expect the midpoint one to be better than the other two. So what do we get? Well, as you can see, the only thing that changes is this sum right here. We still get 0.01 when you add up all of these things. We can factor 0.2 out of all of them. But now what you get is 1.1 plus 1.3 plus 1.5 plus 1.7 plus 1.9. What do you get? These add up to 3. So we get 6, 7.5. So we get 0.002 times 7.5. So we get 0.015 kilograms. It's true it's the average of the other two, but that doesn't have to be the case, that when you take the midpoint one, you get the average of the other, the left Riemann sum and the right Riemann sum. Okay. Which one of these approximations is the best? Well, it will turn out that this one is. I'll say it again. That does not necessarily have to be the case for every function, but it's true here. And we'd like to see that somehow. So let me record these Riemann sums and then look at the problem some more. So I want that the left Riemann sum is 0.014 kilograms. The midpoint Riemann sum is 0.015 kilograms, and the right Riemann sum is 0.016 kilograms. Okay. Suppose we want a better approximation. Well, as I said in the last lecture, it is true that if you subdivide the intervals enough, our density function, I should write this, our density function is continuous. The actual function we're taking Riemann sums of is that times the cross-sectional area. So this is certainly continuous. And what I said is that when you're finding Riemann sums of continuous functions, that if you want the Riemann sum to approximate the actual mass, in this case, to an arbitrary, to within epsilon, you can take the intervals small enough so that regardless of what the sample points are, you can make that happen. All right. So let's see what happens when we change the intervals. It's going to be, I'm going to let the size of the intervals, or the number of intervals, be a variable, which will mean I can't put all this in a table anymore, because we're going to have just an arbitrary number of things. We're going to have to use some of our summation formulas from the last section in the book. But suppose now we take a smaller partition. So we refine, well, I shouldn't say that. This is not necessarily a refinement of that partition. We're going to take partitions with smaller and smaller meshes, so the width of the biggest subinterval will get smaller and smaller. But they needn't be refinements of this one exactly, because we don't necessarily include those endpoints. So suppose we use a partition. We always want to partition the interval from 0 to 1 meters. We use a partition of 0, 1 within equal subintervals of equal length. What will that equal length be? Well, I called it delta x before. It's the total length. Each subinterval would have to have length, the total length, 1, divided by the number of subintervals, so 1 over n. So this means we're taking the partition. Our partition looks like it starts at 0 and it goes up 1 over n each time until you get up to n over n. Well, there'd be an n minus 1 over n, and then there'd be n over n, which is 1. So our partition would look like this. All right. The ith subinterval all right. Let's look at it for a second. The first one is 0 to 1 over n. So this is where I is 1. Then when I is 2, you go from 1 over n to 2 over n. When I is 3, you need to go from 2 over n to 3 over n. So in terms of I, well, you're always going to exactly what I is over n, and you start at 1 less than that in the numerator. So the ith subinterval is you go to I over n, which means that the thing before that is I over n minus 1 over n, so the end point before that. So you subtract 1 over n. So this is the ith subinterval. All right. If we're using left endpoints, so if we're using left endpoints for our sample set, now this won't be, I'm using the same letter because it's going to be the left endpoints of the subintervals. But this, when I wrote it before, was for a particular partition into 5 subintervals of equal length, and now I'm going to do it no matter what n is. So just understand that this is the general case. Here's the ith subinterval. The sample set, the ith thing in the sample set, S sub I, right? So this starts at S1, goes out to Sn. The question is, what is the ith one, where I could be anything between 1 and n? Well, in the left sample set, it's the left endpoint of the ith subinterval, which is I minus 1 over n. All right, and then the Riemann sum for this, the Riemann sum, using left endpoints with that partition of our function f is the sum, as I goes from 1 to n, of, you take f of si times delta xi. This is the general formula. In our case, first of all, delta xi, the width of the ith subinterval, they're all the same. They're all 1 over n. So that part becomes a 1 over n. So we have something here, and then 1 over n. F of si. Well, here's f, but we have to replace the x by si, and si is I minus 1 over n. So what goes here is something I didn't leave enough room for. So what goes here is the 0.01 times 1 plus I minus 1 over n. So that's f of si, and then times the delta xi. This sum is the Riemann sum using left endpoints and partitioning into n subintervals of equal length. And what we suspect, and what I said by theorem, is if we make n large enough, which means if you make the mesh small enough, because all the subintervals have length 1 over n, so the length of the largest subinterval is 1 over n. So 1 over n is the mesh. If we make n big enough, we make the mesh small enough, this Riemann sum will approximate the actual mass arbitrarily well. So as you can probably imagine, we'd like to take the limit as n goes to infinity. But we need to calculate the sum. What happens here? Well, the index of summation is I. Certainly that's a constant. This is a constant as far as I is concerned. Both of those can be pulled out of this summation by linearity. And so what we get for this left Riemann sum is 0.01 times 1 over n times the sum as I goes from 1 to n of 1 plus I minus 1 over n. All right. I want to do, as a kind of separate side problem, this summation. It uses the things that we developed in the previous section on sums and differences. So I'm going to come back up here and fill in some more. But as the piece of the problem that we need to do right now is, what is the sum as I goes from 1 to n? What's a nice formula for the sum as I goes from 1 to n of 1 plus I minus 1 over n? Well, this too you can split up by linearity. It's a sum of things. So this is a sum of 1 as I goes from 1 to n plus the sum as I goes from 1 to n of I minus 1 over n. But again, the 1 over n here is a constant as far as I is concerned. And so you can pull out this 1 over n and get this. Okay, so we get the sum as I goes from 1 to n. Well, let me stop writing that. The sum as I goes from 1 to n of 1. I is 1 and you add a 1. Then I is 2 and you add a 1. Then I is 3 and you add a 1. You keep adding a 1 for every number between 1 and n. You get n. Plus, you get a 1 over n times, well, you can split up that sum. This is the sum as I goes from 1 to n of I plus, well, minus the sum as I goes from 1 to n of 1. Well, again, this part is n. This part we had a formula for in the last section. So we get n plus 1 over n. And the formula we developed for this, it is n times n plus 1 over 2. And then you subtract, this is n. All right, if you do a little simplification, multiply by 1 over n, it'll cancel that n. You'll get a 1 there. So this is the same as n plus 1 over 2 minus 1. And you can get a common denominator here of 2. So this is minus 2 over 2. So this is the same as in fact, why don't I go ahead and write this as this equals 2n over 2. And then here you get a 2 over 2. So putting everything over 2, we get this equals 3n, so 2n plus n, 3n plus 1 minus 2, 3n minus 1 over 2. That's what we get for this sum, 3n minus 1 over 2. All right, so we get this is 0.01 times 1 over n times (3n minus 1 over 2). All right. I have left out an important part of the problem, which I should have, oh no, I'm sorry. No, this is fine. I was looking for the missing point too, but we've taken, okay, our formula was coming out so nice that it was is bothering me. Nope, this is fine. So you get this times this. All right, that is our formula for the left Riemann sum using n subintervals of equal length. What happens here? What you suspect, and what I told you as a theorem, is if you make the subintervals small enough, you can approximate the actual continuous sum, the actual mass, arbitrarily closely, which means what we're interested in is what's the limit, as n goes to infinity, of what we just calculated, of 0.01 times, and now I'm going to use this 1 over n and divide it into each of the terms in the numerator. We get a 3 minus 1 over n over 2. What happens as n goes to infinity? This part goes to 0, and we're left with 3 halves times that. So we get, this is 1.5, we get 0.015 kilograms. So we're getting exactly this midpoint Riemann sum. We're calculating this if we believe that it's okay to take subintervals of equal length, and that if we take subintervals that are smaller and smaller, we get closer and closer to the mass. Then what we've just shown is that, in fact, in this example, the midpoint Riemann sum with 5 subintervals gave us exactly the right answer. That's because we picked a very simple function f. This is a very special case. If you do the right Riemann sums, you'll also get a summation. You can take the limit as n goes to infinity there, and you'll get this also. Is it true that the left Riemann sum will always be less than or equal to this, will always be less than or equal to this? Yes, but that's because our function that we're finding Riemann sums of was increasing, so that the function is always bigger to the right and smaller to the left. So when you take left endpoints, you're as small as you can be, and when you take right endpoints, you're as large as you can be. It helps to look at this graphically. And in fact, not just in this example, but graphically what's going on in Riemann sums and continuous sums is extremely important. It helps you see what's going on very well. So here's x. I'm going to take the function that we're taking Riemann sums of, which is our f of x is 0.01 times 1 plus x. I'm going to not put a scale on the vertical axis, so I'll call it the y-axis, but I'm just going to draw basically a line that looks like y equals 1 plus x, and just assume by a change in scale that it looks correct given for our scale. So this is supposed to be the graph of f of x. Oh, I don't want 1 way over there. Let's put 1 over here. This is supposed to be the graph of this. Okay. What happens with Riemann sums? The diagram gets very crowded if you put in too many subintervals. So let me just put in 3 instead of 5 or more. So let's put in 3 subintervals of equal length. So that would be at 1/3, at 2/3, and at 1. Then you pick a sample point. So if you're picking left sample points, then in this first subinterval, you would pick this left sample point, and you would evaluate the function there. So that would give you this value. And then in that part of the Riemann sum, the contribution from this subinterval, you multiply this height, so the value of this function, which is this height, times this width. Well, that would give you the area of this rectangle, right? The part of the Riemann sum that corresponds to this subinterval, you take the width of the subinterval, and multiply it times the value of the function, which would be this height. On the second subinterval, if you're still using left Riemann sums, you take the left endpoint of the subinterval, you take the corresponding y value, which would be this height, and you multiply times this width. So that would give you the area of this rectangle. And in this third subinterval, you again take the left endpoint, and you go up to the corresponding point on the graph, so the value of that function, and you multiply that times the width of this subinterval. It gives you the area of that rectangle. All right. What happens if you use right endpoints of the subintervals? If you use right endpoints of the subintervals, then on this first subinterval, you use this right endpoint, you go up to the corresponding point on the graph, and you multiply times this width. Well, that graphically, that would give you this rectangle. The pink one is inscribed. The green one is superscribed. It goes over the top of the graph. On the second subinterval, you would take the right endpoint. You would go up to the corresponding point on the graph, but then you multiply times the width of this subinterval, which corresponds to the area of this rectangle. And then finally, on this third subinterval, you take the right endpoint. You go up to the corresponding point on the graph, and you'd be adding the area of that rectangle. So the left Riemann sum in this picture corresponds to the sum of the areas of the pink rectangles, the ones that are inscribed. The right Riemann sum corresponds to the sum of the green rectangles, the ones that are superscribed. Clearly, this area, well, I'm pointing to this that we calculate with 5 subintervals, but clearly this area is bigger than this area. The midpoint area, you would take midpoints of each subintervals, go out to the corresponding point on the graph, and look at this in-between rectangle. So, okay, fine. So that's how the Riemann sums kind of, how you can see them graphically in terms of sums of areas of rectangles. And yeah, if you have an increasing function, right, the left Riemann sum rectangles will always be below the graph. The right Riemann sum rectangles will always be above the graph. The question is, what's this limit that we're calculating? We know that it comes out to be the midpoint Riemann sum, but is that how we want to define the mass? Or was there some other way that we could see it? So let me draw a picture that's less cluttered. Now that that one looks so bad. So you've got this graph. This is, again, supposed to be the same thing. F of x equals 0.01 times 1 plus x. The right, or the left Riemann sums corresponds to this, graphically, to the sum of the areas of these 3 rectangles. All right. We know that our smallest calculation of the mass, because this function is increasing, will occur if we take left endpoints. And the biggest approximation of the mass will occur if we take right endpoints. So the actual mass is somewhere in between, right? It just has to be. If you believe there's something called the mass, and that we're underestimating it when we take left points, and we're overestimating it when we take right endpoints of subintervals, then the mass has to be trapped in between. So what is graphically, how do you see the actual mass, not just the Riemann sums? So the Riemann sums correspond, the right and left Riemann sums correspond to these inscribed and superscribed rectangles. Well, suppose we take more rectangles, both places. Inscribed, so we take left, we refine our partition. Like, so I'll subdivide each subinterval in two, for instance. Then you still use left Riemann sums. So now you get more rectangles. And we hope that our approximation is better, but as I've said before, for a general function you don't know that, but for an increasing function you do. Or if it were decreasing you would know it. It's when it's both increasing and decreasing that you have a problem. But you get, again, if you use left and right endpoints for the approximation, you get inscribed, and what happened right there? You get inscribed and circumscribed rectangles, but what's happening now is the difference in areas between the sum of the pink ones and the sum of the green ones is getting smaller and smaller. Right? The difference in the areas, right, would just be represented by, right, what's the difference between that area and this area? Oh, this amount, this amount, this amount, this amount, this amount, and this amount. It's smaller than when we had fewer subintervals because there were much bigger blobs in the difference. And as you take more and more subdivisions, these superscribed and inscribed rectangles get closer and closer together, and the difference between them gets smaller and smaller. So what is it that the limit is giving us? If we believe there's something called the mass, well, if these get smaller and these get bigger, then what you're approaching is just the area under the graph. Right? If the green ones are always above the graph, the pink ones are always below the graph, but both of them are getting closer and closer to the graph, then in the limit, what you're calculating is exactly the area under the graph. Right? The area is, I'm going to write this, but we're not really going to talk about it carefully until the next section, should be the limit of the Riemann sums, regardless of what sample set you take, as you let the mesh of the partition approach 0. Right? Graphically, this is supposed to be fairly clear. As you take more and more subdivisions, the area of the green rectangles gets closer and closer to the area of the pink rectangles. Oh, we can verify it in this case because we know how to calculate the area of a trapezoid. The area of a trapezoid equals 1/2 the sum of the bases times the height. The bases are the two parallel sides, and the height is this length. So the bases, let's see, when x is 0, we get this point is really when x is 0, so this is 0.01. This is when x is 1, so this is 0.02. So 1/2 the sum of the bases, so this base has length 1, this side has length 0.01, 0.02, and then the height, which is 1, so we get 1/2 of 0.03, which is 0.015. Right, kilograms. That's what we got when we took the limit. We got 0.015 kilograms. So yes, we did get the area under the graph. And you might think, oh, well, then this is how you evaluate integrals. You just calculate areas under graphs. Yes, except we don't know how to calculate areas under graphs. We knew it here because the graph of this is a straight line. But suppose our density had been given by 1 plus x squared, so that the cross-sectional area times the density look like this, well, then we'd be in trouble, because then you need to know the area under the graph of a parabola. And this isn't so easy. Now, it's true, right? It's the limit of our Riemann sums would actually be this area. But how do you calculate that? Now, it's true that for this case, and because we developed a summation formula for I squared, we'd be able to handle this one using our summation formula, and we could find the limit. But what we'd like to do is be able to evaluate these things in general, and it turns out that you do that by using antiderivatives. And the fact that you calculate these limits of Riemann sums using antiderivatives is called the fundamental theorem of calculus. But all the applications come from the fact that you're doing this summing process. You're chopping things up. If you've got a function of one variable, you chop some interval in that one variable up into little pieces, into little subintervals. In each subinterval, you take a sample point. You evaluate the function that you care about at the sample point, and you multiply times the width of the corresponding subinterval, and you add those things together. That process comes up over and over again, and we'll talk about it at length. I'll just make one more comment before we stop with this section on Riemann sums. You might think, okay, we want the area under this graph. Well, you should just be able to do it just by some other calculation. So you pick some x coordinate somewhere. We can certainly calculate, we know the function, so we can calculate this height. Why don't we just add up all those heights? Well, there are an infinite number of heights, and that wouldn't even have the right units. It's not that you add up the heights. It's that you take some subinterval around here. You take a sample point, S, you take some subinterval containing S, and your approximation of the area under the graph in this subinterval, so you approximate this area under the graph on that subinterval, which has a curved edge, you approximate it to be the area of this rectangle that has the same width, but whose height is given by the value of the function at the point, which is what we were doing for the mass. So saying it's the area under a graph doesn't give us a better way to calculate it, well, except in geometric cases like where the graph is a straight line. It doesn't give us a better way to calculate the integral. What it does is give us a better way to, or a nice way to picture it in terms of things that strip away, we don't care, there's no rod here, there's no mass, there's no density, there's a graph, and there's area. And so you've kind of stripped away all the extra stuff and boiled down the problem to something that's easier to talk about. All right, in the next section, we will more seriously take limits of Riemann sums to define the definite integral and look at some results, some theorems about definite integrals.